Suppose we have the titration of a strong acid with a strong base. So the strong acid is the analyte, and the strong base is the titrant in this case. So according to this titration curve, the pH is quite low, and as the base is gradually added in the solution, it increases gradually until the equivalence point is reached, where the number of moles of acid is equal to the number of moles of base in the solution, or the acid is completely neutralized by the base. And a strong acid-base neutralization reaction yields a neutral salt and water. So at 25 degrees, the pH is 7 at this equivalence point. And if we're using the known volume of the titrant, which is the base, for which we already know the molar concentration, we can calculate the number of moles of the base, and then using the mole ratios in the reaction, we can calculate the number of moles of the acid and divide that by the known volume of the acid that's already known to get the unknown molar concentration of the acid. And note that when this jump occurs, the equivalence point is taken in the middle, where this here is the volume of the base that was added to reach the equivalence point. And as more base is added, the base is in excess and you get a gradual increase of pH of the solution. We have a weak acid in an aqueous solution, and that reacts with water to produce hydronium and its conjugate base. So therefore this is a buffer solution. And now we titrate with a strong base, and that'll be neutralized by the acid to produce the conjugate base and water, and therefore the concentration of the conjugate base increases, and the buffer acts to shift the reaction to the left by Le Chatelier's principle and reacts with hydronium to produce more of the conjugate acid. And therefore we initially see the buffer causing a gradual increase in pH, and at this point, which is the half equivalence point, half of the acid is neutralized, and therefore there's an equal concentration of the acid and its conjugate base. And if we're using the equilibrium expression for this reaction, where we have the acid dissociation constant, well, at the half equivalence point, these will cancel, and if we take the minus log of both sides, we can obtain the acid dissociation constant by reading the pH at this point. Now if we continue to add base, the buffer capacity is reached, and all the acid gets neutralized. So you get a jump in pH. And at the middle here of the jump is the equivalence point, where all the acid has been neutralized. So here the buffer is broken, and the volume of base that's added at this point is double that at the half equivalence point. Here we have a buffer solution produced by a weak base, which reacts with water to produce a conjugate acid and hydroxide. And this is titrated with a strong acid to produce the conjugate acid of the base. And through the common ion effect, by Le Chatelier's principle, the reaction shifts to the left to create more base to neutralize the acid. And we can write the base dissociation constant for this reaction. And at the half equivalence point, half the base has been neutralized, so the concentration of the base is equal to the concentration of the conjugate acid. Therefore these cancel, and taking a log of both sides, we obtain the following expression. So we can read the pH at this point, and then use the following expression at 25 degrees Celsius to obtain pH and the base dissociation constant. Now if we continue to add acid, the pH keeps dropping and the buffer gets broken until we reach the equivalence point, where all of the base has been neutralized by the acid. And if we keep adding acid, the acid becomes in excess, and you keep getting a drop in pH past the equivalence point. Consider the titration curve for carbonic acid. So this has two equivalence points, which tells us that the acid is diprotic. And at the half equivalence point, within the buffer, the concentration of the weak acid is equal to the concentration of its conjugate base. And we can also determine pKa by reading the pH of the curve. Now at the equivalence point, all the acid has been consumed, and we're left with the conjugate base. And it's the weak acid resulting from the protonation of carbonic acid. So at the half equivalence point, within the next buffer, the concentration of this acid is equal to the concentration of its conjugate base. And similarly, at this point we can determine the acid dissociation constant by reading the pH. So we'll call this 1 and 2. And at the equivalence point, all the acid has been consumed, and we're left with the carbonate ion being the conjugate base. A 10 ml 1 molar solution of a weak base is titrated with a hydrochloric acid solution. And in part A, we'll estimate the base dissociation constant. So the buffer reaction can be written as follows, where these are an aqueous solution. And from this we can obtain the base dissociation constant. And at the half equivalence point, the concentration of the base is equal to that of the conjugate acid. And using the following expression, assuming 25 degrees, we can read off the pH as around 10, and therefore pOH is 4. And that's equal to minus the log of the concentration of hydroxide. And solving this equation gives the concentration of hydroxide, which is equal to the base dissociation constant. Now in part B, we'll find the molarity of the hydrochloric acid solution, and recalling the neutralization reaction of a weak base with a strong acid, and ignoring the spectator ions and adding H2O to both sides, we can obtain the following net ionic equation. where these are an aqueous solution. So at the equivalence point, all of the base is neutralized by the acid, and we're left with the conjugate acid. So effectively the number of moles of the base is equal to the number of moles of the acid. And that's just another way of saying the molar concentration of the base by the volume of the base is equal to that of the acid. And if we make our substitution for the given values of the base, and the volume of acid that was added at the equivalence point, which is around 9 ml, we're going to obtain the molar concentration of the acid as follows.